This video is going to be introduction to series. Let's start by considering an infinite sequence. So it's an infinitely long list of numbers in a definite order. Then an expression where we add all those numbers, or in other words, we add terms of that sequence, is called an infinite series, or just a series. So series is the sum. And because it's the sum, we can use sigma notation, right? So Greek letter sigma is used to represent sum. And here it says that sigma, it means that we're adding up. A sub n, it means that we're adding up terms of the sequence. And then how many terms are we adding? Well, from the first one to the, well, there is no last one, but there are infinitely many of them, right? So n goes from 1 to infinity. So that represents that infinite sum, which is the series. Now we also have something that's called partial sums. So the partial sums are when we add only certain number of terms. So the partial sum S1, and we denote partial sums by S for sums. S1 represents that we're only adding one term, the first one. S2, the second partial sum, is when we add the first two terms, and you can see the pattern, right? So when we have a partial sum S sub n, it means that how many terms are we adding for this partial sum? Well, n terms, right? And that's what it's shown here, from the first one to the nth term. And I can also write that summation using sigma notation. I am adding, so that's sigma. I'm adding what? Well, I'm adding terms of the sequence, but only from the first one to the nth one. So I'm going to use I as the counter, and I goes from 1 to n. So that's how I can rewrite this using sigma notation. And what's important to note is that partial sums, they form a new sequence, right? Now, A sub n is a sequence, A1, A2, A3, right here, right? That's the sequence. But as we look at the partial sums, they also form a sequence, right? Sequence. And I added this note here, so the partial sums form a new sequence. That's one of the ways we can describe it, or that's a short notation for any sequence. And now here's the question. If we look not at the partial sums, but the entire infinite series at all terms, or the sum of all terms of the infinite series, can that ever be equal to a finite number? If we keep adding infinitely many numbers, can that be equal to a finite number? Well, that's a good question to consider. Here it is. Is it possible to find a finite of infinitely many terms? And the answer is that yes, in some cases it is possible. So yes, in some cases. So for example, if we consider the following series, which is basically the sum of all positive integers, right? What do you think? Will we get a finite number when we add infinitely many numbers like that, so they keep increasing? So I think you have a sense that, well, it's not going to be equal to anything finite. It's going to be something infinitely large, right? So in this case, this series doesn't have a finite sum. How about the second series? It's given to us in the sigma notation. So to get some sense about what it might be equal to, it's better to expand it. Let me remind you, when we look at the series in this notation, then whatever stands inside the sigma represents the nth term of the sequence, which terms we're adding up here, right? So first term, second, and so on and so forth. So let's obtain the first term. It's 1 over 2 to the power 1. Then we need to add the second term. That's 1 over 2 to the power 2. It's 1 over 2 to the third power, 2 to the fourth power, and then we'll continue. Then we'll see the nth term. But then after the nth term, we still continue. It's an infinite sum, right? Let's simplify those terms so it's a bit easier to work with them. 1 over 4 plus 1 over 8 plus 1 over 16, and so on and so forth. So what do you think? If we add infinitely many fractions like that, are we going to get a finite sum? Is it going to be equal to some number? At least what we can observe here that we're keep adding. So in the first example, we kept adding the larger and larger number every time. And this time we're adding smaller and smaller number, right? So 1/4 is less than 1/2. And then 1/8 is less than 1/4. So we keep adding smaller and smaller and smaller number. But to analyze if this series equals to a finite number, we want to look at the partial sums. So the first partial sum is just the first term, so it's 1/2. The second partial sum is the sum of the first and second, 1/2 plus 1 over 4. So that's same as 2 over 4 plus 1 over 4, that's 3 over 4, right? The third sum, let's just do it maybe up to the fourth sum. It's a little bit tedious process right now, but it will help us to see what happens with the series. Plus 1 over 8, so the LCD is 8. I'll have 4 over 8 plus 2 over 8 plus 1 over 8. That's 7 over 8. And then the fourth sum is like that. So let's see, the LCD is 16. 8 over 16 plus 4 over 16 plus 2 over 16 plus 1 over 16. That is 15. 15 over 16. And we can continue, but let's maybe switch to something else right now. So what can we say about the partial sums so far? What kind of result are we getting as we keep increasing or keep adding one new term? So the first partial sum is 0.5, right? The second partial sum is 3 over 4, so it's 0.75, right? The third one is 7 over 8. That's 0.875. The fourth one is 15 over 16. That's 0.9375. So what can we notice? As we keep adding a new term to the sum, looks like the numbers are, well, they're of course increasing. Can you guess or can you predict what those partial sums are going towards? What number? Well, we actually won't be able to tell for sure until we find the nth sum. So let's try to express the nth sum. So how do we do that? Well, what can help us is to look at the terms of the sequence, and they are 1/2, well, partial sum sequence, 3 over 4, 7 over 8, and then 15 over 16. That's all what we got, right? Can you notice a pattern in the partial sums? So what can we say about the denominator? So it's 2, 4, 8, 16. So denominator looks like it's a power of 2, right? Power of 2 that corresponds to the number of the term. So n equals 1, 2, 3, 4, right? So it's 2 to the first power, 2 to the second power, and so on and so forth. So 2 to the power n, where n is the position of the term. How about the numerator? Looks like all numerators are 1 less than the denominator, right? 7 versus 8, 15 over 16. So I think the numerator can be written in this form, 2 to the power n minus 1. So this describes nth partial sum. But we don't want n terms in our partial sum or in the sum. We want infinitely many terms, right? So think this way. We actually want that n to be infinitely large. Well, what this means is that we can now try to set up the limit. So if I try to find limit as n goes to infinity of S sub n. And because we found formula for the nth term of this partial sum sequence, well, we should be able to find the limit. So it's limit as n goes to infinity of 2 to the power n minus 1 over 2 to the power n. To find this limit, I think I will split this expression into two. It's limit as n goes to infinity of, so I'll split it like that. So it's 2 to the power n over 2 to the power n, which is 1, minus 1 over 2 to the power n. And we know that limit of a constant is that same constant, but then what is the limit of 1 over 2 to the power n? Well, the denominator gets infinitely large as power approaches infinity. That means that overall quantity approaches 0, right? As the denominator grows, fraction becomes smaller and smaller, so it approaches 0. Well, that means that limit is 1, right? Limit equals to 1. And what does this mean in the context of our problem? Well, remember we found limit of the nth partial sum letting n approach infinity. So that is what the infinitely large sum equals to. So if we add all terms for the series, then we're gonna get 1. That's what that sum equals to. It's a little bit hard to think how we add infinitely many numbers and we get a finite result. But that's how things are in math, right? But in the case when the series equals to a finite sum, we say that that series converges. So the series converges. And all that is defined and explained in this definition right here. So given a series, let S sub n denote its nth partial sum, right? And that's how it's described. Sum of terms from the first one to the nth one. Then if the sequence of the partial sums converges, in other words, it approaches some kind of number, right? So we find partial sums and we can see that partial sums keep approaching a certain number. It also can be found or expressed using a limit, right? That's what we just did. So if limit of S sub n with n approaching infinity equals some kind of number, it's a real number, then we say that the series itself is convergent. And we can write like that. So we can write an expanded form and say that it equals some kind of number s, or we can write it in using short notation and then set it equal to s. And this number s is called the sum of series. So that's when you find sum of infinitely many terms. However, when the sequence of the partial sums is divergent, right? So it means that as you find partial sums, you notice that they're not approaching one number or they're approaching infinity. So they keep growing and getting bigger and bigger and bigger, or approaching negative infinity. That's also a possibility. So when that sequence is divergent, then the series is also going to be divergent. So that's the definition of convergence and divergence of the series, official definition. I want to finish with a few important notes. So the first notes is just the summary of what we talked about, and it's important to realize that when we work with a series, with any series, it's associated with two sequences. One sequence is the sequence of the partial sums, right? That's the one we just played with. And the second sequence, well, it's the sequence of its terms, right? It's the sequence that defines the series itself. We're adding terms of that sequence. So there are two of them. It's S sub n sequence, partial sums, and then A sub n sequence. That's the one produces the series. That's one. And then here's the note. It's important to know that in general, it is hard to find the formula for the nth partial sum. That's what we just did in our example. Well, it's actually something that's usually very hard to do, to find formula for the nth partial sum so that we can later take its limit, right? So instead, we're going to use learn and use different tests that help us to determine whether a series is convergent or divergent. And we won't need to find a formula for the nth partial sum in that case.